We're going back to class credits fall and spring. And this is another way to do the regression using the data analysis ToolPak. So we have to make sure that in Excel, the data analysis ToolPak is enabled. If you go to the Data tab, it should be on the upper right-hand corner. If it isn't, you have to go to File, Options, at the bottom, Add-ins, then Excel add-ins, and make sure that Analysis ToolPak is marked. First, we're going to make a scatter plot for the X and Y, for the fall credits and the spring credits. We want to predict spring credits from fall credits. So fall is the X, spring is the Y. And it's set up so that X is first. If you mark them like that, insert, and there's the graph. I'm going to put axis titles on here. You make sure the graph is highlighted. Then over on the top left, and there's other ways to do this, you can go to this plus sign, that box on the right top next to the graph, and if you click on that, you'll see the same menu as you do if you go to Chart Elements. Add Chart Elements. We want, no, I don't want Chart Title. I want Axis Titles. Click in one. This is fall credits. And this is spring credits. This is something that is not necessary, but you probably should do whenever you make a graph, because as soon as you move away from it, you forget what it was. And if you come back to it a week later or a month later or a year later, you've got no idea what it is. So it's best to label as much of it as you can. Go ahead and right-click on any point in there. We want to add trend line. And at the bottom of the list in the Add Trend line is Display Equation on Chart and Display R Squared Value on Chart. We want both of those. So this is the quick way to do any of the regression stuff for the simple linear regression in Excel. So we got an R square of 0.62. That means that 62% of the variation in spring credits is associated with the variation in fall credits. And the equation is 0.7589 slope and 2.155. Somewhere in here, calculate the slope and the intercept using the slope and the intercept command, which is equal slope. I didn't get it right. Didn't spell it right. Slope. And it wants known y's first. This is one of the few things where the order matters. That's the slope, and I don't like where I put it. I'm going to put it up here. And the intercept. Intercept command, y values first, then the x values. And those values should match what we've got from the add trend line. 0.7589 and 2.155, and it's got a different number of decimals on it. If you knock it to the same decimals, it comes out to be the same. So there's the slope and the intercept. This is the line of best fit. It minimizes the sums of squares of error, my mistakes in prediction. Go next to the spring credits, and we're going to predict these using the regression equation. Predicted, I guess. That may or may not be spelled right. But right next to each one, we want to put in the slope and the intercept in the equation equals intercept plus the slope times the fall credits. So that 18 times the slope plus the intercept is 15.8. That's what I predict it to be. If you look at the 18 on the graph, the actual value is 12, and the predicted value is at the top of the line there and is at about 16. I got to lock the cell references for slope and intercept. In mine, C9 is the slope, is the intercept. C9 is the intercept, and C8 is the slope. Put a $sign in front of the letter and the number, and that locks the cell reference. Or you can name them. Copy it down. Get rid of some of the decimals. And that's the predicted value. That's the line. So if I go up from fall credits to the line and over to the spring credits, that's the value I would get. Then I'm going to do the residuals. I predicted 15.8. It's actually 12. So I overestimated by 3.8. And the residuals are always calculated as observed minus expected. That means it's observed D12 minus 15.8 E12, and there it is, 3.8 negative. So I overestimated by 3.8. Look at those and look at which one has the highest residual. There's a 5.2, a 4.5. Those are the ones that are furthest from the line. So that the 5.2 is at 8 hours. So for 8 credits in the fall, we have 3 credits in the spring, and it's predicted to be 8.2. So just like in standard deviation, observations furthest from the line have the most effect. Add those up, and you can use sum or the automatic command. And you will get 0. The sum of the residuals is always 0, which is one way to check them. It's useless as it is because it's 0, so we have to square those numbers. This is the squared residual, and it's just the residual squared. The residual squared. Add those up. I'm going to use the automatic sum command. And that is the sum of squares of error, the SSE, the minimum sums of squares of error for the regression. That's how I determine the slope and intercept. Now we're going to do it a completely different way, using the Data Analysis ToolPak. Go to the Data tab and Data Analysis. And scroll down, and there is Regression. So we want the regression command. OK. And it asks for the Y range and the X range. The Y values are the spring credits. I'm going to mark spring credits as a name along with the numbers. So I mark that whole column, spring credits, and I'll do the same for the fall credits. Include the name so you know what you're dealing with. And you'll have to click on Labels because we've got fall and spring credits in the label names. Otherwise, it will try and calculate with that and it won't do it. Need to select the output range, and anywhere will do. What we're going to get is what's on that handout sheet. When you click OK, there is the results of the regression. And this is all the things that the regression has in it that we have calculated in other ways, but it's all right there. And I'm going to knock decimals off because there's way too much stuff there, and it just obscures what you're doing. At the top, the first thing is multiple R. This is useless. Below that is the R square, and it's correct. This is the coefficient of determination, the square of the correlation coefficient. This matches with what we did before. If we do correlation between X and Y, and this one doesn't care which is first. .79 is the R value. If I square it, 0.627 rounded, and that's the value right there. The R, the multiple R that it has there, in this case, matches the correlation coefficient. In other cases, it doesn't. It's a different value, and basically the multiple R is not useful. If you want to get R from R squared, take the square root of the R square. The next one down is the adjusted R. And this is adjusted for the number of X variables that are in there. And this is useless as well. There are arguments to be made for using this, but I don't think they're particularly useful. Here, the next one is called the standard error. And if you expand the column so you can see the titles, this is the standard error of the regression. Out of all the stuff I got left that I don't know, this is the standard error of that stuff. This is the standard error of unknown, of residuals. So if I did the residuals for the mean and variance, the mean would be 0, the standard deviation would be whatever, but if I convert it to standard error, that's what I get. So 3.466 is the standard error of the regression. And this actually is used for all other calculations of variances in the regression. That's the regression statistics part. Go down to the ANOVA. This is the analysis of variance. And analysis of variance is purely, I've got this much difference in these things. How much can I attribute to regression and how much is just plain error? If you look in here, the degrees of freedom for the regression is 1. The degrees of freedom for the residual is 8. We would normally have 9, n minus 1. And the total degrees of freedom is 9. You don't have to worry about these things. If somebody says, what's the degrees of freedom? Look in the table. We lose 1 degree of freedom for every x value we have. So we start with n minus 1. We've got 1x. We lose another one. So we have 8 for the residual. Right next to that 8, this is a sum of squares. If you look back for the sum of squares of error, the squared residuals, that's 96.1. And that's that number right there. The total, I don't know, as a sum of squares. The total variation in all this stuff is 257.6. The unexplained variation, the sums of squares of error, is 96.1. And the number above that is 257.6 minus 96.1. It's what's left. So I've got a bucket full of 257.6 unknown. I take my sponge, I put it in there. When I pull it out, I take out 161.5. And 96.1 is left in the bucket. If you take the regression sum of squares, the 161.5, and divide it by the total, 257.6, that's where r squared comes from. It's the explained variation divided by the total variation. And the mean square in all of these things is the sum of squares divided by the degrees of freedom. So the mean square for a regression is 161.5 divided by 1. The mean square for the residual is 96.1 divided by 8. Go to the standard error of the regression in the regression statistics. Square that number equals 3.466 squared and that's the 12.01. That's where that number comes from. All the things we did involve standard deviation or standard error. When you do it as real statistics, they're variances. They're the square of the standard deviations and the standard error. So that these are variances. Take the square root, we get a standard error. Right here, it says F. This is actually a statistic. This is an F distribution and an F statistic. And in this application, the F is the square of a t-value. So for a t-value, for 95%, 2.5 in each tail, what cuts off that much? What's the t-value for 95% in the middle? That would be 2. If I square it, I get 4. Any F value greater than 4 is significant. We're in the ends. This one's 13.4, and I cut the decimals off of here. If I calculate it or expand it, that's the p-value, which is much less than 0.05 or 0.025 or anything. That number, if it's greater than 4, means the regression is useful. The hypothesis test for that is the null, the regression is no good. The alternative is the regression is good. So with F of 13.4, which is much greater than 4, I reject the null hypothesis and say that the regression is good. If you ever get one of these things and see that F statistic and it's less than 4, that means you wasted your time. And I've seen a lot of people use regressions that have non-significant F values. The regression is no good is the null. If it's less than 4, the regression is no good. You're wasting your time. And people really don't like to be told that. They've done a lot of work, they've collected a lot of data, and they predict one thing from another, and then you tell them that they may as well be guessing. And they do not take that well. So you have to find a way to explain it to them so that it isn't their fault. You don't say, stupid, don't do that. It must be much more careful than that. On down further, in this part of the table, and this is just a copy of what's on the spreadsheet. I'll go back to it. Right there, it says intercept. That's the intercept for the regression. That's what we get with the intercept command or from the trend line. And below it is the slope, which is the same thing we get from the other two places. In Excel, there's 3 ways to do everything. This is the 3rd way to do the regression. The reason it's important that I got it labeled is that otherwise this would say slope. And it wouldn't tell you anything about it except if you knew the fall credits was the X value, you would know that this is the slope. But it's the fall credits and it's the slope. Next to it is the standard error of that estimate. And this comes from the SSE, the mean square error, and it's completely unimportant because it's calculated for you. But we have a test statistic for these. For the intercept, the null hypothesis, for the intercept, the null hypothesis is that the intercept is 0. That the line I put through that data could have easily gone through 0. That's the hypothesis. And it would tilt the line. The t statistic is 0.88, which is much less than 2. In all this stuff, remember 2. That's right out of the empirical rule, the 95% confidence interval. If the t value isn't 2, if the f value isn't 4, it's not significantly different from whatever. This says that the slope could be 0. I can't reject the null hypothesis that it is 0 because it's 0.88. Don't even look it up. It's less than 2. It's gone. In case you need information, there's the p-value for this test, which is 0.41. That's the area in the tails. It's much greater than 0.05. We aren't rejecting anything. Next to that is another way to do it. This is the 95% confidence interval for the intercept. And it includes 0. It goes from minus 3.5 to plus 7.8, and 0 is in that interval. So we've got a test and a confidence interval that show the same thing. Or the intercept could be 0. The only reason to make an intercept equal to 0 is that there is some compelling reason for that. You have a relation where you know that 0 means 0. In this case, we don't have any idea that that needs to be true because we don't have anybody taking 0 credits. Nobody is taking 0 credits by definition. So the only reason to put an intercept of 0 is if there is some reason to do it. And we don't have one. Here's the slope, 0.7589. The t statistic is 3.67, bigger than 2. The p-value is 0.01, which is less than 0.05. The test is the same as for the intercept. For the slope, the null hypothesis is that the slope is equal to 0. The alternative is that it is not equal to 0. And in this case, we reject the null hypothesis in favor of the alternative, and the slope is important. If the slope were 0, I'd have a flat line, and it would mean that no matter what I predicted for with fall credits, spring credits had nothing to do with it. And if you look at the 95% interval, 0.28 to 1.24, it does not include 0. This test doesn't test anything except that is it 0? I don't have a value for it. I don't say it's equal to 1 or it's equal to 0.7 or equal to 0.9. All I do with that test is it 0 or isn't it? And it's not 0. At least according to the statistics. One other, while we got them, We're going to do the same thing for car value and miles from the car data. Car mileage, so forth. So go back to My Open Math. Look at the car data. And we're going to repeat exactly what we did for this. Car miles, mileage, type, and value. And for this, we're going to predict value from mileage. So go right to data, data analysis, and we want to go back to regression. And in the version of Excel I have on here, it doesn't erase what I already had before. So it's going to do the same thing unless I change all of this stuff. I have to erase everything in here, or it will do whatever it thinks is doing. So for the Y range, I'm predicting value, and I want to include the name, the title, the name of the variable in that list. And for the X values, I want to include miles, the title of the variable, the name of the variable in the list, and that labels box has to be checked because I'm going to use that in the analysis. Output range, again, pick a spot. Doesn't matter where. And if you look at the rest of this, look below all the things that we entered, we can actually plot the residuals. We can get a list of the residuals, the ones that we calculated before. We can get standardized residuals, which is another way to look at it. And that's a standardized variable. We can do a residual plot. We can do line fit plots, all kinds of stuff. And some of it's useful, but not a lot of it. Residuals sometimes is useful if you have a reason to work with the residuals. Otherwise, we want X, Y, labels. And if you look at below labels, it has a confidence interval. By default, and if you look at the previous one, for the confidence intervals at that last block, that's 95%. You can specify another level as well. I'll put in 90. And it's going to give me the 95 by default and the 90 by request. Okay, and there it is. All right, here's the trick with the multiple R that I told you was not good. What's the correlation coefficient between miles and value? Is it positive or negative? As the car gets more miles on it, what happens to the value? It goes down. And if you look at the slope, it's negative. This R value that it spits out will never be negative, even if it really is negative. So that's one reason to ignore it. If you ever want the R value, get the R square, take the square root, and apply the sign from the slope. The slope and the R always have the same sign. If the slope is negative, the R value is negative. So if I wanted the real R, I'd take the square root of 0.486, and then I have to put on the negative value. Down at the bottom, I get the same stuff as before. Here, for those confidence intervals, I have a lower 95% and an upper 95%, and a lower 90% and upper 90%. This is the one I get to choose in that setup. Here's the intercept, 28.87. The slope is minus 0.117. Both of them are significant. Here's the t statistic for the intercept, which is 18, and for the slope is negative 5. Both of them are outside of the 2 and minus 2, so they are significant. They're so significant that the p-value doesn't even show for 3 decimal places. Look at the slope. The variable that I'm predicting is value, and it's in thousands of miles. I'm using miles in thousands, so that the slope here $117 in thousands divided by miles in thousands. If I cancel out the thousands, for every 1 mile additional on that car, the value goes down 12 cents. So 12 cents negative. Every change in miles has a change in value of 0.12 negative. So that the slope and the intercept have real numbers in them. And in this case, the relation is negative. The intercept is 28 something. Is there any chance that this could have a 0 intercept? What's the value when the car mileage is 0? Whatever they're selling it for. So it's going to be up here somewhere, so that the 0 cannot possibly be the intercept.